method. You look at exercise 5C, which is to do with functions. Okay, so I'm going to go through function details in detail because this is going to be new to everyone. All right, so we'll get started. So all graphs are known as relations. Okay, so we just have to accept that it's a term we use for any type of graph. They're like a relationship, so that's why we call them relations. Okay, so all graphs are relations. Now, a function is a particular type of relation. Okay, so not um, all functions are relations, but not all relations are functions. Okay, so it must meet a certain criteria. So a function is such that for every x value on the graph, there's only one corresponding y value. Okay, so for every x value, there's only one unique y value. Okay, so it can't have two y values for every x value. Okay, in any part of the graph. So to simply do a test to check whether something is a function or not is when you perform something called a vertical line test. So to perform this test, you simply imagine a vertical line on any part of the graph, and if the vertical line crosses the graph once, then it's a function. If it crosses twice or more, then it's not a function. Okay, so we'll go through that in an example later on. Okay, so I just want you to understand that for every x value, there's y value for a function to be defined. Okay, to exist. So which of the following relations are functions? Okay, so want to check whether they're a function or not, and you want to state the domain and range of each. Okay, so for every x value, so when x equals 0, we have a unique y value. As you can see, A does not work. Why doesn't it work? Because when x equals 0, can you see we have two different values possible for when x equals two different y values possible for that unique x value. So that's not a function. B, we'll have a look. Yep, that's definitely a function because each different x value has a different y value, okay, which works. Okay. C, so that's correct. C, we'll have a look. No, that's not a function as well because even these are two of the same x values, and as you can see, they have different y values. Okay, two different y values. So that's not a function. So cross that out. We'll have a look at D. Yep. Can you see all the x values? All the different x values have a unique y value, so that's a function. Okay. It doesn't matter if the y values are the same, that's fine. As long as the x values are different, then there's no problem there. Okay. So only B and D are functions. Which of the following relations of functions state the domain and range of each? Okay. So the domain, even though that's not a function, this will be a relation. So it's be a relation. Remember, all graphs are relations. Okay, but not all are functions. So that's a function. That's a relation. That's a function. And we're trying to find the domain and range of each. Okay, so the domain will be, it will be a set of numbers because these are discrete points. 0, 1, 2, 3. 0, 1, 2, 3. Fancy brackets, range. Now I won't go for all these, I'll just go for the probably first. The range would be 1, 2, 3, 4. 1, 2, 3, 4. And that's your range. For B, the domain will be the possible x value, so -1, -2. It should be the other way around. Always go to lowest value first. So -2, -1, 0, 1, 2. And the range would be -1 or -2, -1. Oh, there's a -5 as well. Okay, let's go -5 first. -5, -2, -1. 0, 1, 2. -5, -1, -2, -2. And let's try this again. So just make sure you're reading the right values, which I didn't. So range is -5, -2, -1, 2, 4. That should be right range. Okay. So basically, I'm just looking at the y and x values. I'm ordering from smallest to largest. Okay, that's what I'm doing. So for examples, graphical examples, how do I know whether these are functions or not? Okay, if we go back to the first slide, I said that you can do a simple vertical line test. If it crosses only once on any part of the graph, okay, well, if it crosses once, not on any part of the graph, but on all parts of the graph, when I do a vertical line test, then it passes the test of function. Okay, so for example, a linear line is always going to be a function because no matter where I do a vertical line, it will always intersect the graph once. So this is a function. Tick. This is also a function because no matter where I draw a vertical line, it will always be it will always cross once, so it's a function. Now, parabola on side, sideways parabola will never always be a function because what's happening here? Okay, they're crossing twice. They're crossing not here. They're crossing twice. Okay, whenever they cross twice or more, then it's no longer a function where you perform the vertical line. So this is a relation. So you just label relation. A circle or a ellipse will never be a function. So it's a relation. Okay, remember all graphs are relations, but not all graphs are functions. A cubic, so x to the power 3, you'll learn this later. This is also a function. So this is also a function. A quadratic is always a function because it always will pass the vertical line test. So it is a function. So this is the way you test whether something's a function or not, just by imagining vertical lines. And you don't need to go extreme like I did and draw a vertical line everywhere. You just put in your head to go, hang on, will it ever cross twice if I draw a vertical line on it? Okay. If it does, if the answer is yes on any part of the graph, whether it yeah, if any part of the graph crosses twice on the vertical line, then it's not a function, it's a relation. Okay, function notation. Okay, so when we're referring to a function, we usually refer it to a lower, we will usually use a lowercase letter, okay, such as F, G, or H, okay? So we we generally don't use Y anymore, okay? So in function notation, it's just by convention we do this. So to understand functions, we first have to understand what an image and a pre-image is, okay? The reason why I'm going through this is because the text will go through this and you might be really confused about like what's an image, what's a pre-image. So if you think of a normal equation, y equals x plus 1, the x is known as the pre-image, okay, the input, and y is known as the image or the output. So for example, if we want to find the value of y when x equals 2, you have a pre-image of x equals 2. Okay, that's what you sub in. Okay, you sub in the rule. Okay, y equals x plus 1. And so this is the input. And on the output end, you get the value of what y equals when x equals 2. So that's like the image. Okay, so pre-image and image. Okay, it's like a physical example I can give is if I have a magnifying glass and I have a let's say butterfly here. Okay, this is the pre-image. Okay, when I apply a rule, well, not a, well, you can think of the magnifying glass as a rule. Okay, because you're transforming it, you're changing it, you're changing the image. You get output, and you know when you see the butterfly, it's bigger. Okay, so that's the image, and that's a pre-image. Okay, that was your original picture. This is your now your picture. So when you put the X on the microscope, you get the Y value sort of. Okay, probably not the best analogy, but that's the way I like to explain it. Okay, so proper function notation. So in in function notation, instead of y, we usually write like this. Okay, so instead of y, we usually, in place of y, we usually write f of x. So f of x equals x plus 1, where f of x means a function of x, okay, which makes sense as the value of y depends on the value of the function. Note, f of x does not mean f multiplied by x, it's simply a notation we use, okay? So if I want to write y equals x squared plus 1, then if you change to function notation, then you write the function in terms of x with the rule x squared plus 1, or something like that, okay? So you're simply moving away from y equals to f of x equals, okay? So to figure out values of a function, we can still sub things in. For example, if I want to find the value of the function when x equals 2, then you simply write f of 2. It means in place of x, we want 2. Okay, so remember our original function was given by f of x equals x plus 1. Now, if I want to find the value of the function when x equals 2, then you simply sub in 2 in place of x. So originally we had x here, now we sub in 2. So whenever we had a x, we sub in 2. So is f of 2 equals to 2 plus 1. It's like saying if I have the equation y equals x plus 1, when x equals 2, then when we sub in that in, we get y equals 2 plus 1, which equals 3. Okay. Instead, I'm using the function notation because you need to learn this notation. I know we're comfortable with y equals. Okay, we're moving away from using y now. So we'll do some examples on how to um, manipulate this. So here's an example. If I have f of x equals 3x squared plus 1, then f of negative 3 means we want to find the value of the function when x equals negative 3. Think of it like this. If x equals negative 3, then what does y equal to? Okay, so all I'm doing is I want to find the value of the function when x equals negative 3. So in place of x, I sub in negative 3. Okay, so in place of x, I sub in negative 3. So instead of having an x there, we have a negative 3. Okay, plus 1. So it's no different to like you subbing in an x value and finding the corresponding y value. Okay, so negative 3 squared is 9. 9 times 3 is 27 plus 1 equals 28. Okay, so f of negative 3 equals 28. So we can still use this notation to find x values, solve for x. Okay, so for example, if I want to find when f of x equals 3, this just means we want to find the value of x, which gives the function a value of 3. So we know f of x equals 3x squared plus 1. Now we know now that f of x equals 3, so we're trying to solve this like that. Okay, so what I'm doing now is I'm rearranging the equation because f of x is now 3. Okay, that's what we said here. Okay, it's like saying when y is 3, what does x equal to? Okay, so if I subtract 1 from both sides, I get 2 equals 3x squared. Divide both sides by 3. 2/3 equals x squared. X would equal plus or minus 2, plus or minus root 2 and 3. Okay, so we need to understand what that actually means. So we can do a few more examples. Okay, so let's have a go at some function notation questions you might encounter in the textbook. So for example, if I want to find f of 3, it just means what is the value of the function when x equals 3. So I sub in 3 for x. Okay, so whenever I have a x, I put in 3 instead. So 3 is a 9, 9 times 2, 18, 18 plus 3 is 21. Okay, f of negative 2, so I'm subbing in negative 2 in place of x, minus 2. So 4 times 2, 8, 8 minus 2 is 6. Now, f of x minus 1, don't get put off by x minus 1, okay? So what that basically means is instead of x, instead of what we originally had, which was x, we have now x minus 1. So for every x that was originally there, we sub in x minus 1, okay? So can you see originally we had a 2x squared, so this would be 2x minus 1 squared now, okay, plus x minus 1. Okay, so what I've done is I've replaced the x with x minus 1. Okay, that's simply what I've done. So that's what function notation actually tells you. Okay, so in place of the x, I have x minus 1. So I just expand simplify. So that would be, if I expand the brackets, that's x squared minus 2x plus 1 plus x minus 1. So that's 2x minus 4x plus 2 plus x minus 1. That equals 2x, 2x squared minus 3x plus 1. Okay. Similarly, if I have f of 1 on a, now instead of f of x, we want f of 1 on a. So all I'm doing is replacing any x's with 1 on a. Okay, so you do it like this. 1 over a would equal, now originally that was x squared, so it's now 1 over a squared plus 1 over a. Okay, so let's expand this. That's 2 over a squared plus 1 over a. I'm not sure whether the book simplifies this, so I assume what they did was they combined the denominators to make it 1a squared. Now that's, if I were to change 1 over a to being on a squared, then that must be an a, okay? So this will be 2 plus a on a squared, okay? I'm assuming that's what they've done, so I'll just leave it like that, okay? So I'm hoping you get a rough idea of how you use function notation. I think the confusing part is how do I use it properly, okay? So let's do like one or two more examples, just so we're clear on how to use it. Okay, we'll go for this one. Okay, we'll go for this one. So consider the function defined by f of x equals 2x plus 4. This is a linear function, basically, or linear equation, if you think of it. And we can see that x is an element of all real. So it means that our domain, or the range, or not the range, but the x values allowed is unlimited because x can be any number on the number line. Okay, so we have three ranges. So f of x, the function f of x equals 2x minus 4 can be any value it wants to be. Okay, or can be any x value it wants to be. So I want to find the value of f of 2. So I'm subbing in 2 basically into the function. So let's work that out. That's 4 minus 4, which equals 0. F of t. F of t means in place of x, I put t. So there'll be 2t minus 4. Find the value of x for which f of x equals 6. Okay, so when it's like saying when y equals 6, what does x equal to? So can you see if f of x equals 6? Well, f of x is here, so it equals 6. 2x minus 4. I solve for x. So 10 equals 2x, x equals to 5. Find the value for which f of x equals 0. Okay. Now, if you're thinking clearly, that's actually asking you for something special. What's f of x equals 0? Well, remember f of x is like my y. When y equals 0, what do we get when y is 0? When y is 0, we usually get the x-intercept. Okay, so that's one way of saying what is the x-intercept of the graph, or how do I find the x-intercept of the graph? So f of x equals 0, so when f of x equals 0, we want to find the value of x, which gives you that. Okay, so 4 equals 2x, x equals to 2. Okay. For what values is f of t equal to t? So we know f of t equals 2t plus minus 4. We worked it out before already. We want that to equal t. So 2t minus 4 equals to t. Solve it. Okay, so I move the t to the left-hand side, so they'll become one single t. And I move the 4 to the other side, it becomes positive 4. So t equals to, t equals to 4. Next question. for what value is f of x greater than x? Okay, so f of x happens to be 2x minus 4. When is it greater or equal to x? Okay, so you just solve it. Okay, it's just a normal linear equation. So I move the x to the left hand side, so that becomes x. I move the 4 to the other side, so x is greater or equal to 4. For what values of f of x is less than or equal to 3x? So 2x minus 4 is less than or equal to 3x. Okay, so I move the 2x to the other side, so it comes x. X will be greater or equal to -4. Okay. Now I did say on the slide, how do I do it on CADS? Now I want everyone to, pay attention to this. Okay, so if I go on to my CADS, you can define a function. Okay, so this is how you define a function in the CADS. Okay, so I want you to follow this really carefully. So you're going to type in the equation. Okay, you're just going to type in the equation with x's only. So you write 2x minus 4, and you're going to go highlight it, and please write this down in your notes. Highlight it, go interactive, define. Now it's already given you a function name default by default f. Okay, that's fine. Okay, we'll use that. And the variable is x, which is correct, and the expression is 2x minus 4, and click OK. So it's defined. Now, what can I do once it's defined? Well, a lot of things actually. You can go onto the keyboard and you'll find on mat 3 there's an f there. If I want to find f of 2, it actually works out that that equals 0, which is what we calculated by hand. Okay, so as you can see, f of 2 equals 0. F of t, so if I go f of t, let's see what happens. 2t minus 4. Yep, that makes sense because we replace the x with the t. Okay. F of x equals 6. So f of x equals 6. Now, it's not going to do anything if you press enter because it just basically writes the equation. What we're trying to do is we're trying to solve for x. Okay, so all you have to do is go interactive, advanced solve, and you get x equals to 5, which is what we got here. So x equals to 5. Okay. F of x equals to 0. Okay, so if I change that to 0, it gives me x equals to 2. Okay. For what values does f of t equal to t? Okay, so f of t equals to t, and you're solving for t, then you get t equals to 4. Okay, so it just works It just works as you normally would think of it working. It's just that we're using some fancy notation here. Okay, f of x equals to x, interactive and solve. Okay, x is greater than or equal to 4, which is what I got there, and less than equal to 3x. Okay, x is greater than or equal to -4, which is what I got here. Okay, so hopefully that gives you an idea of like how to sub in stuff on using function notation. It's not that difficult. It's just getting your mind around it. Okay, so that's the CADS part. You can do it by hand or by CADS. Now, fully defining functions. This is really important because in the textbook, they'll start using this type of notation a lot, and if you don't get what's going on, then you could be forever lost. Okay, so to define a function, you usually have the name of the function at the front. So this could be f, g, or h. Okay, and then colon means such that the domain of the function. Okay, so what's the domain of the function? What's the natural domain of the function? Okay, mapped into. So this means mapped into reals. Now it's always going to be mapped into reals, so that's a given. So all you need to know is domain mapped into reals, comma, then the rule of the function. And the rule of function is always in function notation, the f of x equals da, 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 okay? Or g of x equals da, 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 or h of x equals da, da, da. So for example, if I want to define a function, y equals x squared, then f, which is the name of the function I've given it, f is, so I've just given the name f, such that the natural domain of x squared is just all real numbers mapped into all reals. So what the mapping means, this is known as the codomain. Okay. What the codomain means is like a canvas, like where you putting the canvas. So reals into reals makes sense because we're using the maximum possible canvas, which is all real numbers. Okay. Now in methods, you don't need to worry about any other thing than reals for the codomain. Okay, so that avoids confusion. And then my rule. So instead of y equals x squared, I have f of x equals x squared. Okay, that's my rule. So let's have a go at this. We want to rewrite these in function notation. So I'm going to call this f. Remember, I put my domain. The domain of a linear graph is always going to be reals, and I'm going to map it into reals because that's always been my codomain. Then my rule is just f of x equals negative 3x plus 2. So you're just replacing the y with the f of x. For b, the set of coordinates such that y equals negative 2x plus 5, x is greater or equal to 0. Okay, so this is already the domain. You just want to write an interval notation, okay? So you just go f such that my domain is greater or equal to 0. So um, you can rewrite that as, remember, all positive numbers, okay? Now we're including 0 as well because we've got the equal sign, so reals union with 0 mapped into reals. Okay, where was mapping into the reals for a codomain, then f of x equals a rule. Okay, pretty straightforward. Now, C is a bit more complicated because we've got y equals 5x squared plus 6, and we've got a restricted domain. Okay, now, so all we have to do is, that's my domain. I know that if I write the interval notation, it's between -1, including, and 2, including. Mapped into reals, such that our rule is given by 5x squared plus 6. Lastly, we have a truncus. Okay, our domain is any value of x except 2. So reals excluding 2, mapped into reals, f of x equals 1 over x plus 2 squared. We're done. Okay, so that's basically a crash course into functions. So hopefully that helps you. Now, I know you will get stumbled into problems, so more than welcome to email me any questions you have. And look, I am expecting a few, and that's okay. This isn't easy to get the first time, but look, I do want you to have a go at it and ask questions later.